Well, I just received this circuit board. It is a arcade board, a JAMMA board that plays lots of pirated NES cartridges or games. Some enterprising hackers dumped some games, threw them on EPROMs, made up some hardware, and allowed you to put money in to play these games. So I'm not 100% sure how this board works yet, but we're gonna find out. It came with a piece of paper here. And the piece of paper just explains what the pots do and what some of the dip switches do and all that. So the guy was pretty nice giving me that. And so what I'm going to attempt to do is reverse engineer this board. I'm curious to see how they've done everything, you know, what registers they added, what they mapped in, and all that. Because I'm also kind of curious how they hacked the games to make them take money now, because apparently this has been hacked so that you can put money in, and then when the game ends, you know, you game over, it actually detects that and, you know, goes back into some kind of attract mode. So since I don't have a JAMMA connector right now, I'm going to order one, but I'm going to actually hook this up. I'm going to solder some wires to the chip pins on the bottom so I don't damage anything, and I'm definitely not going to solder to the JAMMA connector. But looking at it, it looks very simple. This board outputs RGB and composite sync, and it does this by taking looks like an NTSC Pirate NES chipset, and it outputs NTSC, and then there is a UPC 1372 that converts it to RGB. So here I'm going to remove the camera here, and I'm going to zoom in on this board. I'm going to point out all the things I see. Okay, so here's the board, and I see it. If I can get a little better lighting here. Yeah, that looks pretty good. I'll get my shadows on there. Okay, so you can see the board here. The things I noticed right away on this board, there's a UA6527. This is a Pirate NTSC CPU. There is a UA6528, and this is a Pirate NTSC PPU. There's this chip with a scratched off part number, and this is an MMC3 clone. There's another PAL here. It looks to be, what, 4, 5, 6, 7, 8, 9, 10, 11, 24 pin. It's probably like a GAL 22V10. There is a PLSI 1016 programmable logic device here. And then there is a TIB PAL 16L8 right here. And the rest is all just TTL logic. There's a 6264 RAM, another 6264, and then there's a sticker. I'm going to take the sticker off using a hair dryer to heat that up, and it should just pull off without any damage, and I can stick that back on when I'm done. And then we're going to dump these EPROMs here. There's 10 of them. Most of these are 27040s, which are 512 kbytes, 4 megabits. There's 4 here, and another 3 here, and this is a 010, which is 128 kbytes, and then this one is an 020, which is a 256 kbyte. So, and then this is a 27C512, I think. Just regular 27512. It's 64 kbytes. And I've had a little poke around on this board, and I have this Pirate Super Mario 3 cartridge here. You can see that. And this is the board that's inside it. And this board here has a Pirate MMC3 on it. And it's got ROM, and this is a RAM chip, and this is a 139 selector. And what's interesting to note, there's actually a row of holes right here. And if we flip it over, there is another set of unused holes along the inside. So what this is for is this particular board can take 2 different brands or styles of Pirate MMC3 that have different pinouts, but they both function the same. So I poked around on this board with my multimeter and found out that the chip with its part number scraped off is the same pinout as this unused set of holes. So what I did, I used this board to reverse engineer the pinout of this chip. And so I have a spreadsheet open, and I'll show that in a minute, but the spreadsheet actually has the pinout that I gained from this from this board, and then I compared it against the arcade board, and they appear to be a match. All the CPU control signals and the PPU control signals all line up perfectly. So I'm fairly confident that I know what the pinout of that chip is with its part number scraped off, and that's why it's really stupid to scrape part numbers off of chips. It just makes someone like me all the more interested in exactly what that part is, and by going by the pinout I can figure out what chip that is and all that, and this was no exception. So anyway, I'll get these out of the way, and here's that little paper he gave me again. Shows that there's volume control, video color, which is probably like a tint control. Looks like there's a sound volume control there, and the dip switch settings. There's an 8-position dip switch there. So we'll go through that when I get this powered up, and we'll figure out what all these dip switches do maybe. In the back is some Korean architectural drawing. So back looking at the board here. Looks like we've got, I was just going over the pinout on the JAMMA connector. So these 8 along here are your controller inputs from directionals, buttons, start, coin up, and all that. And I noticed this little ground wire they added here for some reason. I think that grounds, that's the video ground, I believe is what that is. And then we got two 4021s, so these are going to be the same exact chips that are in your NES controllers, and they're performing the exact same function on here. There's a 74LS244 8-bit tri-state buffer, and that's actually hooked up to the dip switches, so this chip is how they're reading those dip switches. We got two 74LS368s, and these again are doing the exact same function they would do on an NES or a Famicom. This is your controller inputs. Then we got two 74LS161s. I'm not sure what these are doing yet. There's a 74LS32, a 139, and this is hooked up the same way it is on an NES or Famicom to select the cartridge and the RAM and the PPU. And then here's our TIB PAL 16L8, and the 16L8 PAL, fortunately, since it's the L version, it has no register, so this is just logic. There are no latches or registers in this part, so that'll make life a lot easier. And then we got two 74LS373s, and these are 8-bit latches, and it appears the code can write to these latches and select all the various modes and things. So these two chips are going to be very important when it comes to how this board actually, say, enables this MMC3. It appears that, going by the games on here, this has some MMC3 games, MMC1 games, and maybe some like UNROM games. So we'll figure out how they actually select all these different mappers. And we got some 74LS157, a 153, 153, 153, 153, 157, and 157. And these 7 chips, 1, 2, 3, 4, 5, 6, 7, are what are going to most likely select between the various mappers. And so I highly expect these 7 chips to be connected between all these, this, and this, and this, and the upper address lines on these EPROMs. So we'll make sure that that is actually what's going on. So. And then under here, under this label, I'm not sure what's under here yet. It looks like this is a RAM chip. I think this is a RAM chip, and this is probably, let's see, 4, 5, 6, 7, 8, 9, 10. So this is a 20-pin chip, so it's probably like a 373 or a 244. It may even be another PAL. So we'll get that label off, and we'll find out. Here's another 157. So there's no less than 8 chips that are multiplexers. So the 157 is a quad 2-to-1. The 153 is a dual 4-to-1. And there was quite a few of each of those. So there's 1, 2, 3. There's 4 of the 153, which is a dual 2-to-1, and then there's 1, 2, 3, 4 of the quad 2-to-1s. So we'll figure all that out. This PLS 1016 is a little CPLD. I looked this up, and I don't know if it's dumpable. I'm gonna assume that this PAL, this GAL or PAL, and this PLSI part are undumpable, so we're going to black box reverse engineer them. So it doesn't matter that they're undumpable. We don't need to know that. Using a logic probe and some other code that I will write, we'll figure what all these things do. And then of course there's a 64K RAM, another 64K bit RAM, so that's 8K bytes, 8K bytes. I'm sure that's probably what this is. And I'm guessing this is the 2K RAM for your name tables, just like on the NES board. And it looks like what they have done is they've got this 8K RAM that they're mapping in instead of the 2K RAM that the NES normally has, and they may be using this extra RAM for their variables for the actual like bookkeeping. So like when you put a coin in, the RAM location that's going to hold where how many coins you put in is going to be, you know, in the upper 6K of this 8K RAM. So I'm not sure which RAM does that. We'll figure it out. And also notice this. It looks like pin 25 of the RAM chip here, it didn't make it through the circuit board, so they just bent it out and soldered it to the top of the board. That's really high class right there. I don't know if you can see that right here. And the other thing I noticed, there's like solder on this point right here. It's kind of hard to see. And it looks kind of like it's been reworked. And then here's that green wire. So here's that green wire they've added right here, and that's just going out right here to the ground where this capacitor should be mounted but isn't. Another little go over on the board here. I didn't mention this. To get this board JAMMA compliant, what they have done is they have this UPC 1372C, and what this is an NTSC video decoder, and it outputs RGB video. So they're taking the output of this UPC 1372, and then it basically connects to the board here. And I notice there's all these resistors and transistors, so I'm not sure. It's possible this chip is outputting component, and then they're using these transistors and resistors and such to convert it to actually into RGB. So I'll pull up the data sheet for this chip, and we'll actually go over it and see what this chip actually does. If it outputs RGB or if it outputs component, whatever it does, we'll figure it out. And then there's a 4066 here, and I've determined what this chip does. This actually shuts the audio off from the CPU to this is the audio amplifier. So it actually shuts the audio off, so when the game is, you know, in attract mode or whatever, it's silent instead of like playing whatever sounds the games normally would play in attract mode. Then there's a 74LS06, and as far as I can determine, basically what this chip is doing is it's just buffering the composite sync, so that'll be the H and V syncs together, and that just comes out one of the JAMMA pins. And of course there's a 3579545 color burst crystal for this decoder, and I mean that's a dead giveaway that this is obviously some kind of video decoder. And then we got our 2147727 here, which is just the crystal that the regular NTSC NES chips use, the PPU and the CPU. Little transistors are making an oscillator for it, and you know it's very similar to the circuit that's actually on the NES board or the Famicom board. And so I mean that's pretty much the overview. So I'll cut to actually dumping these EPROMs. So I got the old hair dryer out here. So basically all I'm going to do, I'm just going to turn this on and heat up the label. Okay, I heated up the label a bit, so now I'm going to see if I can get this label off of that damage. Oh, the label looks like it's trying to fight me. I guess they design these labels so they don't come off, because, oh no, you might actually try to return your pirated arcade board. Yeah, I'm sure the manufacturer honored their warranty on their pirate boards. Might be able to get it. No. Oh well, I tried. Yep, 6116. Yeah, and that's a 74LS373. So I got the label off, such as it was. So I'll clean the board up. To clean the label residue off, I'll use a little isopropyl alcohol that I got at the store. This is 91%. Now all those chips should be a lot easier to read. So it looks like we've got a 6264, which I thought that's what that was, and a 6116 like I thought, and then a 74LS 373. Next step is to dump the EPROMs. So what I'm going to do, I got my EMP20 here, I got the board, and I got a little thin client running FreeDOS, and my little thin client's right here. And basically what I'm going to do, I'm going to just dump these EPROMs bottom to top, and they have a part number on the board underneath each chip, I believe. So get into this. And start with the EMP20 software. Unfortunately, this programmer is a bit old, so I have to run it through DOS, and it uses, yes, the parallel port. So first thing I'll select my device. I'm just going to say generic. I'm not programming, so that's good. So I'm going to select 020. That's the first EPROM. Get that out of the socket here. And it says ROM 13. So I'll put this in the socket there, and then dump the device. And it says it's dumped. So since this is called a ROM 13, I will call it ROM 13.bin. And let's save it. There, it's been saved. So now the next one, pick that one out. The next one is marked ROM 12. So, really? I don't know if you can see that, but pin 31 of this EPROM has been fixed. They have soldered a part lead onto pin 31 of that EPROM to fix it. I saw that when I was looking over the board earlier, but I didn't know exactly what that was. It merited a second inspection, and sure enough, that's what they have done. So it looks like all the EPROMs on here are all different brands. There's like a AMD, an ST, another newer AMD, an Intel part, another Intel part, a TI part, and that's a AMD part. So it looks like they just took whatever random EPROMs they could pull off other arcade boards to make these. Very classy. So now that since this is a bigger EPROM, this is an 040, I'm going to have to select 040 like that, and then we'll make sure it's securely locked in, and just hit the button twice. And now it's reading it. It'll take a while, so we will skip ahead as I read all of these. I'll just go. Yeah, the legs on this EPROM are pretty bad shape also. This one's been soldered to, and it looks like, oh, that's why it was so hard to take out of the socket. This EPROM has actually been soldered into a circuit board before. I don't know, it's kind of hard to see that, but you can see where one pin's kind of been soldered to. And dumped. Unfortunately, I'm going to have to do this quite a few more times. So this is ROM 12 that I just dumped, so I will change the file name to ROM 12. Why it saves files this way, I don't know. It's really stupid. There. So before I go any farther, just to make sure things are going along well, I am going to inspect the ROMs that I've just dumped. So that was, this keyboard's horrible. What do I call that? ROM. Oh, there they are. So, yeah, looks pretty reasonable to me. Yeah. One fairly sure way is to look for the vectors at the end of memory. It's like they're vectoring low high 0050 5010 FEOC FEOC 0C 48 8A. Yeah, I would call that. Yeah, it looks like the data looks on a first pass looks pretty good, so we'll look at this other one here. I don't know what's up with that. Yeah, I guess that could be. Yeah, I guess that's valid. It looks like it's got some vectors there at the end. 5010 again, C074 and C0C2. Yeah, vectors look fine. What's interesting is the reset vector points to 5010, which is most likely this smaller EPROM, so that'll be very interesting to see what's in that. I'm guessing that this EPROM doesn't have a lot of data in it because I kind of cheated and poked it, and this EPROM is 64K and it's actually mapped into the entire 64K address space of the CPU, but obviously it's probably only enabled for, say, the 5000 range, so we'll find out when we get there. So I'm guessing a lot of this EPROM is actually going to be empty. So I'll go back here and continue dumping since it looks like it worked. And this EPROM appears to have been previously used also. It has been soldered to a circuit board and then desoldered, and the pins have been cleaned up a bit and they've stuck it in a socket. So yeah, I'm only going to pop out 2 chips at a time, one that's being dumped in the next one in line because I don't want to screw them up. They're not marked. However, I was looking kind of carefully at them, and it looks like someone may have written in pencil on them, possibly. Reading ROM 10, so that's 3 of these are done now. Yeah, and this EPROM has also been soldered to the board. There's extra solder on the pins on the bottom. So they've just desoldered these and reused them. And this one's marked ROM 18. That's interesting. I should write that down. So there's 10, 11, 12, 13. This one's 18 for some reason. Maybe this is for a different mapper. Maybe these 4 are for like MMC3 and this is for MMC1. So always document. Amusingly, that's interesting. There's some very scribbly writing on the bottom of that. Also, interestingly, this is marked IC36, while the rest of these are marked ROM and then a number. Kind of hard to screw up which one that is. This is 27512, so I got to select 27512 and plug that into the programmer socket, read it. And that was called IC36. That. And this to his, I'm not sure. No, maybe that one hasn't been soldered to a circuit board. Leads are kind of fairly clean. This is an interesting EPROM. It's one of those really big windowed ones, so it must be pretty old. Copyright 1990, but it was actually made in 92. So it's got one of those real big windows. And this is an 040. That is ROM 17. So I'm guessing it goes 10, 11, 12, 13, 14, 15, 16, 17, 18 is what I'm guessing the order is going to be. Next EPROM is actually a 27C010, so I will have to change that after I save this. So this was ROM 16. Another previously used EPROM. It had been soldered to a circuit board. And yes, that is ROM 14. So now we know what all the designations are. This is the last one. It's another 040. There. All EPROMs have been dumped, all 10 of them. So now I just got to save that last one there. And get out of this. Take a look at those ROMs. There they are. ROM 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, that looks pretty good, and we looked at that one already. So 11 should be new. $5010, C169, 5450. So that would be the NMI reset and IRQ vectors, and they've repointed two of the vectors just like you would expect. So I would say the data in there looks pretty decent. Do it again on this one. Contra. That's pretty good. You can see where it says Contra right there. So we got 5010 again, C060, C0B5, so that looks good. And then 18 was the last one. Yeah, that looks pretty good. 5010, C0F6, C0F6. So that looks good. So those ROMs look fine. And then so the last ones are graphics, so these won't be. Yeah, that looks like NES graphics. Yeah, that does too. Oops, if I select the right ROM. Yeah, that looks like NES graphics right there. That does also. So. And then, as I suspected, the little 64K EPROM is mostly empty, so we'll probably see code around 5,000 hex. There's a little more code in there than I was expecting. Looks like I see a character set fly by there. So let's look at 5,000. I'm guessing 5,000 is where a bunch of that stuff is. I don't actually see anything at 5,000. Oh, wait a second. Yeah, we do. Yeah, here we are. So 5010 is where all of those games vector their reset to, and 5010, 5,000 is where the code starts. So 5010 is D878. How about that? That's clear decimal flag, set interrupt flag, and then A20 is to load X with 0, and 8E0. So it looks like they are clearing RAM, and then loading the stack pointer. So yes, that's obviously the reset code. So going through here, see if I can see any interesting strings like, and I can't, if you can see that, it says credit right here. Yeah, credit to continue, insert coin, push start. Insert coin, push start. Just a bunch of random stuff. That's amusing. Programmed by Sang Ho Engineering, KB Kim, 1986-11. I highly doubt that this was actually programmed in 1986. Maybe they meant 1996 because the dates on the chips and the little sticker said 96, so I'm guessing they actually meant 96. I wonder if there's some way to make that actually come up on the screen. I bet there is. Looks like a character set. Maybe, yeah, it looks kind of like that's a character set right there. Everything's in groups of 8. So this is probably uses that character RAM. Just more random code and data. And that's all that's in there. So now I'll copy these onto my USB memory stick. And then I'll be able to get them onto my big computer. And that's the ROM dumpage. So now I will go back and we'll hook this up and see if I can make it work. So now that the EPROMs are dumped and they're safely on my little flash drive here, I can actually go ahead and start doing a little more heavy-duty reverse engineering of the circuit board itself. So I've looked over it some more, and I mean, it looks pretty basic. I don't really see a lot of difficulty in figuring out how this is going to work. So what I've done now, I opened up a spreadsheet and I have actually pinned out 3 of the chips. I've pinned out this scratched off MMC3 clone, this TIBPAL 16L8, and then this PLSI 1016. And the PLSI part's only about half done, but from what I can see, I believe this is actually emulating MMC1, going by how it's hooked up. And this is obviously an MMC3, and I'm not sure what IC24 is. I'm guessing it's just some glue logic, and this PLSI part also has some glue logic in it, and then this PAL here is just simply address decoding. So this most likely is what's decoding those 5,000 hex addresses, because I'm guessing these registers and this tri-state buffer and this register are mapped into the 5,000 area. So what I can do now that I've got this dumped, I will disassemble the code, and I will be able to go through the code and actually see what they're reading and writing to. And then what I can do is I can put my own code in here, and with a little monitor program and through a serial port and terminal, I can actually probe this and figure out what they're doing by actually using a logic probe. I could use the logic analyzer or the oscilloscope, but I think the logic probe will probably be the best way. So I should be able to write to addresses and actually see these pins of these chips, these latches, go high and low. So that'll be kind of interesting to see. But first, I should probably power this up and see what it's actually doing. And what I can do is, since I don't have this JAMMA connector here, right here, and it'll take me at least a week to get one, what I'm going to do is I'm just going to solder some wires to the bottom of the board here where it's not really going to hurt anything, and I can take them off without damage, and hook it up to my power supply and hook it up to a monitor. And I was looking, and this appears to take 5 volts and -5, and looking at the -5, it appears the -5 is only used by this amplifier chip. So I can do that. Actually, I think that's 12 volts. But in any event, it's only used by the audio amps, so That shouldn't be a problem. I'm not going to be amping the audio. In fact, I'll just hook a wire up here to where the audio comes out, and I'll hook a wire where the video comes out, and I'll just use the usual AV circuit and see what happens. So to get this board here hooked up to the monitor, I have my little video circuit that I made. It's just your standard 1 transistor circuit, and that will hook up to the PPU here to get the video out. I got my RCA cable that plugs into the monitor, and then to hook this up, I'm just going to clip lead it like this and hook it up to that video circuit. But before that, now I gotta get power on this board. So what I'm going to do, I have this my power supply here. It's kind of off camera a little bit, but I will get some wires on that power supply and solder them. I'm going to solder the wires onto the board and connect them to the power supply, and then we'll see how much power this thing draws. Everybody should have a nice big fat roll of this telephone wire. I think it's solid core wire. It is, I believe, 24 gauge. Yeah, 24 gauge, 4 conductor. It's called cross connect wire, I believe is what this is called. Anyways, it makes excellent wire for doing things like this because it's not stranded. So, and it's got a nice PVC jacket on it, so that means it's not going to melt. I'll get a good little hunk of that wire there and strip the ends and solder it to the circuit board on the bottom, so we're not going to damage the card edge there, because I'm definitely not going to solder to that. So I think I'm probably going to solder right here because these are nice and big, and that's where the power normally comes in anyway. And I can just put a little solder on the bottom there. So I tend to use the white wire with the white on it is the positive, and the darker one is the negative, which in this case is orange. So put a little solder on the bottom there. This. There. So now I got power wire connected, and what I'll do, just to make sure after I strip the ends here, I will use the multimeter here in continuity mode, and I'm going to say that this orange wire is going to be ground. And it is. And the white wire should be 5 volts. And it is. So I'll hook these up to the power supply. Like that. And just because, as I always say, check multiple times. So I'll put this in the ground of the power supply, and we should connect to the minus side of the chips. 5 volts, connect to 5 volts, and it does. So I've checked 3 times now to make sure I'm not going to blow up this nice little board. So the next step is we gotta get video out of this, and pin 21 appears to run all the way over to the circuit board, and it comes out right about here. So what I'll do is I'll get the meter again, put it on pin 21. I mean, I can grab pin 21 right here. It's kind of hard to see, but it comes out over here also. So I think I'll just attach it right there. We got 5. I need 5 volts and ground anyway, and those should be fairly close. So I gotta remember how this works. Oh yeah, red is 5 volts in this case. And video comes out right here, so solder the red to 5 volts. So I need 5 volts and ground, so I am going to pull those. Here's 5 volts. 5 volts is available right here. And then pin 21 is right here. So let's solder this right here. Then ground, I have to find ground. Ground's right here. And I'll verify this with the meter after I hook it up just to make sure I didn't screw anything up. And this ground's kind of hard to solder to, but it'll go. There we go. So ground is this. And ground's being very tricky. So now I'll hook a wire up to connect pin 21 to my circuit. And again, I'll use my telephone wire because this stuff is awesome. Tin the wire. And solder it to that pad, that via, and then hook it up to the transistor base where it belongs. Whoops. And video is hooked up. I don't know, it may be a bit dark depending on how much load is being put on the thing there from the circuit on the arcade board here. So the next thing I'm going to do, I'm going to make sure I hook this up right. So I'm going to again check ground here. So this should be here, and 5 volts should be here, and it is, and they're not shorted. And then this should be pin 21. It is. So this, I'm going to see if this is ground or not. I don't know if it's ground. Oh, it is ground. Okay, good. Because what I'll do is I will use that as a convenient ground point. Let's connect that like that. Actually, I've already got the clip lead on there, don't I? So this white clip lead is the ground of this RCA jack, and the red will be the hot of this RCA jack, like that. And then I will plug that in here, the output of my video circuit, and we should be good to go. So I'll turn the monitor on here, and we should be line. I'm not sure how that works because it's not labeled very well. And I will turn the power supply on. And it's drawing 680 milliamps at 5 volts. Yeah, that's probably about right. So it should be working right now. And it is. Look at that. It's playing. It's kind of hard to see, but it is actually playing Super Mario 3 right now, just like in the eBay auction ad. Let me try the new Tetris. I wonder what that is versus like old Tetris. Really? Oh, the graphics are all hosed up there. Oh. Really? That's interesting. That's such a new Tetris. Some money in there. Fighter. And then attack. Oh yeah, Russian attack. Yeah. And then fighter. Number 18. Oh, it's Rygar. Wonder which version. It's kind of hard to play it though. And you have to be able to press 2 buttons at once. Game over. Huh. You only get 1 game of Rygar. Oh yeah, that'd be pretty fun. So yeah, the board appears to actually function mostly properly, so it actually runs at least. And then those chips get really hot too. So what I'm curious about is these are the UA 65, 27, and 28, and Jason let me borrow this other set which is marked UA 65, 47, and 48. So I'm curious what the difference is. I think I'm going to pop those in the sockets and see what happens here. So I'll start with the PPU. I'll just put it in. See what happens. Yep, it seems to work. Colors are screwy though, so oh, that's interesting. I don't know why. Maybe this is a PAL part. I don't know. That's really strange. I'm not sure. It appears to function though. That is weird. But if it's PAL, it's got NTSC timing. So that can't be right, so I don't know. In any event, it appears to function, so I'm going to say that the board is actually functional, even though it looks like some of the games are kind of screwy, but I don't know if that's just because they hacked the games or if there's actually a problem like these EPROMs aren't in the right order. I'm just not 100% sure on that. I mean, I guess it's possible there could be some other problems. But yeah, those chips are pretty damn hot. So here's a good close-up of the board with my little video hack going on. So we got the UA 65, 27, and the 28, which are the Pirate NTSC CPU PPU. Then we got our MMC3 clone, which has had its part number scraped off. Another little programmable logic device, the PLS I1016, and our little TIDPAL 16L8 right here. And then everything else is just like, a lot of this is just your stock stuff you find on an NES board, like that crystal there. Here, that's your stock crystal, a little oscillator made out of these transistors. The 4021s, which you'd find in your NES controllers. And the 368s, which you'd find on your NES board. And the little 64K bit RAM chip, another one. And I mean, that's pretty much everything that's on the board there. That's your, they'll have your name tables in it, and then there's some for character RAM for games that need that. And then another little latch, and then the video decoder here, which takes up a surprisingly large amount of room. So the UPC 1372, we'll look into that later. And the 4066 here, that's turning the audio on and off so it can mute this when the game isn't being played. And then here's your audio amp. And then that's pretty much it. Just proof that it's working. If I put some money in, it should go back to the Super Game List. Super Game List. And so then you use the A and B buttons here to select which game you want, and then you hit the start, which is here, and it plays the game. And I'm just using a wire here, the resistor lead that's grounded, and just touching the edges here to start the game, because there's 8 connections along the top. So you got looks like select, start, you know, up, down, left, right, and then B and A. And that's pretty much it. And the bottom of the board has 6 more connections. It's just up, down, left, right, and A and B for player 2. And I mean, that's basically it. And then your video comes out these 2 pins, and there's 2 more on the bottom, and that's your amplifier output, 5 volts in, 12 volts in, and that is basically it. It's actually quite simple, so I should be able to do, now that I got everything dumped, and once I reverse engineer this all the way, I should be able to make an NES image of the ROMs, and it should be playable on some emulators once someone implements the mapper, that is. So that's it for this first part. So I'll do a little more work on this and show off how I did that. So the next step, I think, is probably hooking up a UART to this board and then writing a little monitor. I actually have the monitor, so I just need to write it onto an EPROM, and then we'll poke it, and I'll get the logic probe out in the oscilloscope and see if we can figure out exactly how this thing's working. So until then, that's it. So I should have another video up pretty soon about the HDMI analyzer. I know a lot of people wanted to see that, so I'll have that up in a little while. So until then,